everyone. Welcome to our molecular nanotechnology session. So, let's start with a quote. Again, from Eric Drexler from Engines of Creation. Imagine a world where the gadgets and goods that run our society are produced not in far-flung supply chains of industrial facilities, but in compact, even desktop-scale machines. So I think the field of molecular machine is pretty broad. There are long-term goals of the molecular nanotechnology kind. And I'm really, really happy to discuss the whole breadth today with a really, really wonderful panel. Thank you so much for joining. Stephane, I think many of you may have seen a lot of him online. He has given a few wonderful presentations about his work. Larry over there, hello, thanks. And we have Erik Benson, another Foresight fellow, Alexis Courbet, who's given absolutely fantastic presentations at workshops and virtually. And then we have a Lee Cronin clone over here. So thank you so much for coming, Dean. And you can bridge between perhaps like, between Lee and David as well. Okay, cool. First question, again, like in the last panel, if you just want to bring people up to speed, what has happened in your field in the past 5 years? How has it changed, and what are you really excited about going ahead?
I begin? Okay. Hi. Well, I think it's been rather continuous. I don't think we've seen quite the adoption of like ChatGPT in like nanoscience, molecular manufacturing. We have some huge advances like in protein design, protein folding. I don't know exactly when the baseline is. Like, is it last year or a few years ago? Like, maybe you've heard about AlphaFold, so protein structure prediction. Now, the people at DeepMind created a lab to do drug design, isomorphic labs, and they're starting to do the generalization of protein folding, like protein folding and drug designing at the same time. It's crazy. So, but I think it's coming up. It's not like a step revolution last year. It's like more coming up, and I think we're going to see incredible things.
Okay, so I work with DNA nanostructures, a bit of RNA also. I'm excited about things that are moving. I think it's coming a lot like kind of dynamic structures that can respond to things. And I'm also excited. So a lot of people worked before building kind of the biggest, most complex structures possible that are very static. But then I think it's very interesting to do very small things. And things like PCR, bridge PCR, lamp amplification, they're essentially a form of DNA nanotechnology, but they're developed without kind of these insights of how the structure actually work. So I think there's a lot of space for improvement by just like designing individual strands really carefully or evolutionarily selecting them to perform their jobs much better, because it's really impressive that they can do what they can do with this very, very crude design. So that's something I'm excited about.
Okay, so I'm going to talk about the perspective from the field of computational protein design. So as you all know, we have these incredible machines that evolved in nature over billions of years, and they actually work, right? It's like the only examples we have. Like in your bodies, you have proteins that transfer information, process energy, and do these incredible things. And I guess now it's the first time we actually have a window into designing those from scratch, right? So biology and computational protein design now allows us to really manipulate this information in silico and design new machines from scratch. And so I think it's a very game-changing approach for molecular machine design.
Hi everyone. So my background, I spent about 5 years in the labs of Dave Lee, and I enjoyed that time. Those past 5 years, I found a huge change and growth of our designs coming from the labs of the Lee group and from Stoddart's group and things like this. The molecular machines that come out, which are not, they are certainly inspired by what biology creates, but they are much smaller in design, much simpler in function. They're trying to prove the principle. And we're seeing that every year a new idea comes out, which is simpler, smaller, more effective. It's got a better method of correcting for errors. That field, I think on an organic chemistry perspective, which is my background, is still phenomenally driving forward. What I've moved towards now, as we were just talking about, is now I'm in the field of automation, and I want to see the idea of, in parallel, we've been so able to design machines that can automate the synthesis of these things. Can we bridge these gaps together? Can we have machines that now make machines in a very Drexler-esque fashion? How far can this go? Can we let it all be run automated in a fashion? That is effectively what biology is doing quite on a daily basis. It's making repairing modules, it's making ATP synthase, it's making further things down the line go. And I think there's a great benefit for that to inspire ourselves and take inspiration from what biology has been doing.
Yeah, I mean, I think we've seen a ton of progress in this field. I'm always just like blown away. I think really at how fast progress is happening. And I think also how undercover to the general public it's kind of occurring. Because I think the things that the field is able to do is like absolutely looks like magic to me on the outside as an amateur. But I think it's progressed a lot. But do you think that we're getting any meaningfully closer to something like molecular manufacturing? Like, do you think A, it will ever be possible? B, do you think it will be possible by just continuing the progress that we're already doing on different approaches, or do we need a foundational breakthrough? What do you think about like the old long-term goals of molecular manufacturing? Feel free to also take it.
Yeah, maybe I won't begin.
Yeah, I can. I have conflicting opinions on this one. So having had to do it myself in my PhD and a bit of a postdoc, it's challenging. You know, we sell a good dream. We want to get there as quick as possible, but we are limited. We don't have the error correction mechanisms on a molecular level. Biology has these things. It evolved them and it made them perfect, effectively. The mechanisms for that are tremendous. What we have in the lab is a system that is flawed. There are problems. We can't control every single atom as we wish to right now, but we will get there. It will just take time. We need to develop a new mechanism for those systems. Instead of using carbon, hydrogen, nitrogen as our system, if we've got different elements in there, different functional groups that are completely abiological, we need to figure out what those correction mechanisms would be because we can't use what is already there. So it's a learning process. It will take time, but I do definitely believe we'll get there. Just the random walk of how we get there in that time may be a little bit challenging. Yes, exactly so.
Yeah, I guess the other way to go about that is to reuse natural machinery for manufacturing, right? So cells are little, factories, and we can just give it like some information, DNA, and ask the cell to create whatever structure and machine we want to build. And that's been extremely successful over the past decade. And that's very scalable, right? Because organisms are all around. They can produce, massive amounts of materials, and so you can design, these things in a computer, then pass it to organisms for fabrication. So that's a very scalable and powerful approach for fabrication.
Yeah, I think I agree. It's this kind of tough questions. What do we want to make? And so seeing kind of Drexler vision with these perfect atomic gears. Like, can we make that? I don't know. Will we ever be able to? I don't know. And then like, why should we do it exactly like that? So I think you have to ask, what are you trying to make? And then work backwards from that. What should the design look like? Through the question of what could we most easily make? What can we manufacture that can have that performance, that can do the task? And I don't know what the task is exactly that we're trying to do in the end, because like an enzyme is a molecular machine that performs kind of single atom chemistry and whatnot. But so maybe we should make synthetic enzymes, but for what? I'm not completely sure what we're trying to do. Yeah.
So yeah, in my case, we approach that from a computational point of view, and we try to make platform that's agnostic. So we don't really know at all who's going to win the race to make atomic precision manufacturing. So there are fantastic approaches from protein design, DNA nanotechnology, even AFM based. But it's pretty hard to see who's going to win. Each has pros and cons. It's unclear if it's going to be a mix or one is going to solve everything. Indeed, we don't need to make to imitate a bird to have flying machines. So yeah, it's still unclear if we're going to have one day nano gears like Drexler envisioned, but we could have protein-based gears who are tetramers and interact with other proteins and then are used as enzymes to make small molecules that go somewhere in a factory. Still unclear. It's very exciting though.
It is exciting. At our workshop this year, we basically had mostly people really kind of designing potential molecular manufacturing architectures. Some were molecular 3D printers, then we had molecular Lego and so forth. And they did that really by also combining many different approaches. And they're not all, I guess, exclusionary. Some of them are potentially complementary. It's still really early, but at least a few of the architecture designs were really promising, I thought, and also quite pretty cross-cutting across the different subfields. So that was really exciting. And I think to your point of what's the point? What do we want to make? Well, I guess one point of it would be pretty general purpose, which is also, I guess, the problem, because I think Adam Marvelstone once pointed this out. He was for any specific application that you want to have or any specific problem that you want to solve, there's always a different way to do it rather than the very hard molecular manufacturing route. So that's why oftentimes it makes more sense to actually do it the quick way. But then, we have these like more perhaps general purpose tools kind of like that are left in the quicksand. But with that kind of like caveat aside, like are there specific applications or fields that you think that will be most impacted by the stuff that you're working on in the future? Like, is it mostly health? Is it material science? Is it energy? Which fields do you think will be massively influenced by the stuff that you're working on? Let's say perhaps in the next 5 to 10 years.
Yeah, I'll give that a good go. I think smart materials for artificial molecular machines are the real place to be. I think the biological molecular machines will have a swathe of uses in health because they are already ready to go into the body and they already got a home there that they can live in. What we're more interested in is just interesting materials that can adapt to different stimuli. They could change different properties, detections. I think there's already a few examples of those already where if they are detecting small bits of gas, these machines can switch stimuli, switch positions and give you a really dramatic response to that, even at the tiniest amount of the analyte that it wants to detect. They're really cute applications, really interesting. It's just how you get them from being published in a nice scientific journal somewhere to actually being applied. That, I think, is where we've got a big disconnect right now. And it's one of the, maybe a spoiler for my real politic tomorrow. I just don't know how we get past that. We seem to just get to the point of publishing and go, look at this really cool thing. Right now, who takes on? If it was that amazing, why is it not in our shoes, in our watches? Why is it not there? And there's just something that we're still waiting on, I think, for that bit to occur. I don't know if anyone agrees.
Yeah. So, just as far as like protein design is concerned, I think that can really impact all of biotech, right? Because it's the first time we have a real information technological window, right, into biology. So we can really manipulate biological information in the computer and create new molecules from scratch. And that can be applied for any kind of like technological applications, I think, in biology.
Okay, yeah. So with DNA nanotechnology, I'm excited about making really small and simple structures that we can use to study biomedical questions. So I'm interested in mapping transcriptomics right now, and possibly I'm also interested in diagnostics and like possibly therapies, DNA-based therapies. I think it's an interesting approach. Yeah.
So I would say all of them. Of course. No, I'm super optimistic. But so what we're seeing already, and that's fascinating, is that you can, like some people have done this and it works. You take a graphene sheet, so just flat surface of carbon atoms. You put a linker and then you attach an antibody to that. And the antibody is specific of a spike protein. And and you put a current that goes in the graphene sheet, and the resistance of the graphene sheet is changed depending on whether the spike is attached to the antibody. And so you make a very sensitive nanosensor. And so we are already seeing a few, so it's still like startups that are getting funding, have made proof of concept, and want to make more, to get more funding to do it at scale, but it works. And that's super impressive. That's fascinating. And it's like this mix of material science, biology, electronics. That's really exciting.
Well, so what do you think then is, you already touched on this a little bit, but to foreshadow some of the things, that we can also talk at length more tomorrow, but I think it's useful to name it. What do you think has been, the problem really with like this research not advancing perhaps as fast as people thought back then, right? I think this is really one where people were so ambitious about this field so long ago, right? Or at least within Foresight, they truly were. And, there's a bunch of different factors that I could name, but I first want to hear from you guys, like, what do you think, has kind of like gone wrong, or like what do you think like we could improve in terms of a more like either social discourse or funding structures, you name it.
Yeah, it's a really great point, and I would like to touch on a previous one as well to answer that. Nothing has necessarily gone wrong. It's just parts of academia, and it's that people don't share their ideas. They don't collaborate with those ideas very much. We have different PIs for love or hate them, and they have their own styles of doing things. And some of them may have the best machinery in the world, but they don't collaborate very much with another team. So we end up just having these channels, and it's like trying to use a screwdriver to hammer in a nail, like just because that was our way of building it. That is the one thing that can be overcome. If people start collaborating and using these different components together, you end up with a Swiss Army knife. It's now got all the different tools in one machine that can solve that problem and that problem, and then you become quite interesting. Where another problem, which will bring my bias in my current role, organic synthesis is not easy. Making these compounds on a 10, 12 step scale is never going to be easy. It's never going to be to convert that to an industrial scale to make loads of it. And then there's always the little secrets of organic synthesis. One group made it this way. They didn't tell you the full thing in the SI. The SI is not completely descriptive. The lab notebook may not be completely detailed. There may be little gaps here and there. How do we solve that problem? And that's an area which I was really interested in, maybe chat with you a bit later about. We're trying to investigate now these ideas of take all of those synthetic procedures that you have, convert them into some standardized code that is run on our machines, actual big fume hood scale machines. Let the machine do that bit. Let it leave no area for translation errors or something that a human might read that slightly differently when you added 10 times this. Was it 9 times or 11 times? No, just let it be a computer written code that will make you that molecule exactly as it was, and then send that file to another person in Canada or wherever. They can make the same molecule, exactly the same yield, exactly the same amount and purity. There was no option, there's no opportunity for a miscommunication or a little bit of something else. And then we start letting machines go between labs directly.
The computing paradigm, I guess.
There you go. I may have given it away.
Yeah, so I very much agree with that. And I guess I think there are, fundamental limits to fabrication that we maybe not always, talk about. So I think there's no like Swiss Army knife for like fabrication for like, everything. But I think chemistry is very efficient at like making, small molecules at the scale, right? I'm not sure, I'm quite skeptical of like scaling that to like machines are like thousands and tens of thousands of atoms, just because, I've done chemistry before and there's like a yield to any reaction. And so that imposes physical limits on what we can manufacture. Although it's very powerful for like specific applications. And then biology on the other side is like, it's very scalable. It's very powerful, but also it's very soft, right? So there's other disadvantage to that. But so I think we'll have to be very specific about what we want to build for what application with what methods, and there will be like, like a very large toolbox of different approaches for creating nanomachines.
Yeah, Ben always said like you have to make the tools to make the tools.
Yeah. Okay. So I'm going to do the standard thing. I'm going to complain about funding incentives and.
Great. Bring it.
Yeah. I mean, it's like even a long grant is like kind of a 5-year horizon, and then you sort of have to say what you think you will make, and then if you're smart, you're always going to choose a low risk track where at least if it kind of fails, you get something out of it. And I don't think anyone wants that for like everyone. Thousands of scientists just taking low risk approaches everywhere. So I think. For more progress, I think we need to fund people longer with more support and more allow people to fail and try difficult things. And collaborations also is kind of impossible. It's impossible to collaborate with other scientists because you have meetings, you agree to things, and then you meet again 3 months later, and like one team didn't do what they agreed to, and then it's like there's no way to push them, and you can't live with collaborators and you can't live without collaborators. It's very difficult to do science for big questions. And then, I think incentives is very tricky. We talk about what can we make, how should we make it, but the risk is even then we're sort of creating roadmaps and we're forcing people to think in certain ways and then kind of reduce risk. And yeah, it's a really difficult problem to solve. Even if you have a lot of money. I'm not sure how to structure a grant program to get people to do the right things.
Do you want to comment on this too?
I don't know. I think it's mostly human nature. It might be physics. Maybe things are not possible, but it might be also human nature. Like I teach computer science, and we force students to do projects in groups of at least 10 people to show them that programming is not the most difficult part. It's like organization, collaboration, communication, deciding what to do, the emergence of tech leaders besides actual supposed leaders. So it's human nature, maybe.
Wow, that would be a big one to solve, you guys. Well, I think, also the point that you brought up is quite interesting of like, the things being downstream of funding, because, if you actually want people to work on something like molecular manufacturing, you probably need an outside organization, something like an Altus Labs. And, we all know at Marvelstone with the FRO efforts, like focused research organizations, thinking of like a different type of institute that would bring people together from different academic labs, either as advisors or like full-time, to actually kind of like combine their methods into something that is more outrageous, similarly or like as outrageous as molecular manufacturing. And so that would definitely be something. But then you also need to signal to them that funding is sustainable. If people are going to leave their tenure track positions, how is that going to work unless you actually can signal to them that this is now a new thing that they can do. And then obviously I think all the things that you mentioned about like incremental research being like a thing that people just like want to see, also to get their citation scores up and so forth is a big one. And we're going to dive into a lot of that tomorrow as well. I just want to know if there's any questions from the panel before we're going to hit a few of the manifold ones. Questions, comments? Yeah, you go and then we go over to you.
Yeah, so how much do you think that greater access to space and doing these things in a gravity-free environment will play a role in the work you do?
My gut feeling to that is relatively little. For these artificial molecular machines we have, they are playing with Brownian motion. They're being bombarded by molecules all the time. The gravity of the effect is not too much, if I'd say that by gut. So yeah, that'd be my one. That's what we have to deal with. Enzymes and other biological systems have controlled that problem in some respect by being such large molecules that can absorb those tiny bombardments, and they are compartmentalized and they are rigid structures that can be controlled in other ways. With our small ones, which are maybe 100 carbon units long at most, they're getting thrown around. It's just a constant bombardment down there and it's crazy. So to try and get directional motion, to try and ratchet that work and get something useful out of a stimuli, like I sprinkled some energy in there, and can you now turn the gear cogs 10 times? There's 1,000 ways it could go wrong. So I don't know if gravity necessarily is going to be much of an effect on that one.
I was just going to ask, I don't know, I don't keep up with this field enough, so maybe this is a dumb question, but is anyone working on the obvious like molecular printer is like the ribosome, right? So is anyone working on a ribosome that can print other things, like not traditional proteins, but let's say any non-sequential polymer, like a different non-sequential polymer? You go.
Yes, that's been coming out of our labs a few times. They are not complete packages, but they certainly can make certain non-natural protein sequences, or maybe that's a bit of an stretch, maybe 6 or 7 together.
Not amino acids at all, but just other.
Yeah. We have these. I can send you a few of them, but they are quite well spread. From our lab or from my old lab, they were just termed synthesizers. They could be anything. They could make helicenes and have them come off this track. Then you could isomerize them late and form this really beautiful structure at the end of it. You can change whatever that R group is on these motifs. It could be any application you wish for. So that is already a developed thing. But bear that in mind, they are smaller. They can only do 3, 4, 5 units. But the idea then is that you have 2, 3, 4 of those machines in solution, and they work cooperatively. So they're all going down their track, making their 5 oligomer units, and then those 5 join up together after the end of that and make a 25 one, and then you could have lots of them working in solution. But that's really hard. Like, so many things could go wrong there. Instead of having A, B, C, D, E, you could have A, D, E, F. It's just which order does it come into? And that's a problem that we're fighting right now. And it's something biology has succeeded in doing, but it's also biologically driven.
Well, I guess like I'm not sure exactly what you're asking, but like if you asking like, can we make a machine that like reads a tape essentially and then assembles like molecules by reading the information from that tape, which is what ribosomes are. It's extremely hard, right? But people are working on that, yeah, absolutely, and that would be game changing.
We had one. This report is not out yet. It's one of the only ones that isn't here yet, but it's a Google Doc still. And at the last workshop, people worked on like the normal like a big printer, then the molecular breadboard idea, and then almost going back to the artificial ribosome. So there'd be at least a little bit of a write-up of people that worked on this whole workshop and try to make it work. Alex, and then we're going to go to Manifold.
Going back to the example of the graphite, could you explain a little bit more deeply what the application is of those sensors and how those sensors are being used?
Sorry, the COVID sensor?
The graphite,
Yeah.
What is it sensing?
The spike protein.
So is it a COVID test?
Yes, it's a COVID test. So the company is called Graphheal, like GRAPHHEAL. And it's former physicists who were working on nanosensing technologies, and they created a startup, Graphil, that does that. So it's like a COVID test. And the thing is that since it's current-based, you connect that to a smartphone, and you have an app like Bluetooth sensor, and you check whether a sample contains spike proteins or not. It's like a mix between biology and electronics, material science. I think it's fantastic.
Let's maybe go through a few of the manifold questions, and then we'll see how we close it out. So again, another reminder, please get on manifold, start predicting and add your own questions. First one is, we should focus more on this area for molecular manufacturing, DNA nanotech, protein-inspired approaches, STM, AFM, or combining a subset of these approaches into more general architectures, which got the most votes. Do you guys disagree? Do you agree, disagree?
Yeah, I think I voted for that one already. I think it has to be all of them. Everything we choose to do is inspired by nature. We're constantly scrolling through what biology or the latest biofields and saying that is an amazing machine. How can I simplify that? What's the periphery that I can cut away to allow me to make it? As you said, we can't go above, a certain size limit. It's just not physically possible in a lab to make bioinorganic chemists. It's just going to take you too long and be a waste of resources. But if you can make it in a biological setting or can adapt it somehow, you're onto a winner with that one. And I'm sure there's inspirations you can get reverse-wise from the small molecule machines that can apply to the big ones as well, maybe.
Yeah, I think I totally agree. And I would say in the short term, there's no need to replicate billions of years of evolution, right? We have this thing that works very well to print molecule at the atomic scale. So let's use it, I would say.
Yeah, no, I agree. But then at the same time, as Stephane said, we can build machines that fly without wings, and obviously we can build planes that fly faster than any animal and cars that drive faster than any animal. And I guess protein designs, anything that's in nature is incredibly constrained under the conditions that it can be assembled. It needs to fold transcriptionally somehow, and it has to work in this kind of aqueous solution. So there must be a lot of space of things that is better but could never be assembled in a cell. So I think it's interesting to pursue also.
Yeah, I just want to add. So that's a very good point, and I think so we can learn from biology, use the principles, but go completely synthetic, right? So for example, the idea of using a polymer that folds is extremely powerful, right? Because then you can precisely position atoms in 3D, with incredible accuracy, and that's the reason why nature uses that, right? Nature doesn't really print, atoms one at a time. That doesn't really make sense, right? The folding process is extremely powerful again. And so we could make polymers that fold that are not based on biological building blocks, for example. So there's a lot of things we can learn from nature and do de novo.
Cool. Okay. Let's maybe put on a very different head. People have been excited about molecular nanotechnology, but also worried about the risks. And for some better or worse, different scenarios. But I think that has definitely been one, I think we all remember, I don't remember when it was published, but the Bill Joyce article, Why the Future Doesn't Need Us, on Grey Goo, and then, that becoming a big spook, and then the Drexler-Smalley debate on is it even possible to do this? So I think there's just been a lot of individual bits that have been holding the field back to some extent, but I'm curious if if you think that we should be already thinking ahead in terms of the risks that some of the molecular nanotechnologies that you're developing could be presenting, and if so, if there's one that you think we should be particularly worried about. There's 3 of them, which is one democratization of weaponizable technology and potential conflict. This probably includes also potential bio or chemical risks, or economic and societal disruptions of cheap production. And then the Grey Goose scenarios almost got no vote. So at least that's pretty good. Is there anything that you think we should be addressing already up front, where we can have maybe a differential technology development approach for building safety and security enhancing technologies first? Or
yeah, I think I lean towards more the kind of safety aspects, not from my own field, because I think we're a little bit away from, I don't think we're going to be causing anyone any trouble anytime soon, but there's so many advances that are being made in the biological molecular machine world, and they are tremendously powerful, and they could be applied with people with bad motives in other ways. I'm not saying they are, but you can see the potential for that happening because it's so already amazingly good at its job, and you can change genes, you can splice and edit them and do whatever you like. It's a wonderful tool in the right hands, and maybe that could be an issue one day.
Yeah, it's a huge problem, and people are very well aware of it.
Yeah.
Right. So, and actually, 2 weeks ago, at the Institute of Protein Design in Seattle, we hosted like bioterrorism workshop because like so protein design traditionally has been pretty inefficient and pretty hard, like so very expert, right? And for the past 2 years now with machine learning, you can design with like much better success rate, efficiency, and it's very easy now. You can just like go on GitHub, get the code, and design proteins in your garage. And so it's a huge problem, and so we don't really have solutions so far, apart from just simply controlling gene synthesis, because it's kind of like the Achilles of like bioterrorism right now. But we're starting to think about not releasing models anymore, because it's getting too powerful, and so in the wrong hands it could be very, very dangerous.
I agree.
That's good.
Same.
Okay. Double plus one. All right. Well, then I guess we only have 3 more minutes left. Is there another question? I think you had one earlier. Why don't you?
Yeah, no, I'm changing the question with the last question.
You may.
So, but this security question, do you think that it is conceivable that, things actually do get that chaotic and the only way to keep up is more like computer science and computer security approach where you patch things, and that there's a healthcare system that allows us to roll out fixes for emerging biosecurity threats to the population? Is that conceivable?
I mean, I really like this analogy, and yes, I fear we might be someday in some kind of cyberpunk world where we patch ourselves with a CRISPR-like technology or molecular machines, and yes, so that might be a fight. That might be in a long time, though.
So are you suggesting that like someone will like make a virus in their garage, then you just like release a vaccine essentially on the fly? Yeah, I mean that's a solution, I guess. It's pretty terrifying.
But your proposal was then, that's come out in the news. You can just go to the local healthcare center and like, this is the antivirus. You just download it, stick it on your arm, get going. See you later, high five. Yeah, that sounds amazing. I'm all for that.
That's scary.
Yeah, and then, like I said, the opportunities for that are endless. It could be anything. It could be, going crazy and you're watching The Matrix and you're downloading Kung Fu. You just put it into your arm and like, I can now fight this disease. I don't have this anymore. We kind of already have a little bit of that when you go and get a vaccine for something else. So we have that bit, how it expands and flourishes onwards. Yeah, it could be a very exciting future.
But maybe those like rapid deployment safety machines become a new source of bioterrorism because it makes it easier to make these proteins and genes locally. So I don't know.
Well, I guess it's always an offense-defense race to some extent. And I don't know if some people are probably familiar also with Kevin Esfeld's work and security DNA and so forth at MIT. And I think he's like trying to kind of like, I guess, stop it more at the source. So I think we need all of the different approaches. Once it's out there, like let's fight it. Maybe if we can prevent it from getting anywhere, that would also be useful. Okay, we almost have no time left. 1 minute. So I really would love for you guys to tell us, in a second, we're going to start the speaker meet and greet. What is a thing that you're really burning for that you think you really, really want to discuss with people? Something perhaps like, that is a field that you think is undervalued, not discussed enough, something that they can really deep dive with you on.
Do you want me to go first? Your time is valuable. Automate everything. Don't do it manually anymore. That's my dream. I work on that as much as possible. I was so tired of doing the organic chemistry back to back to back every single day. It's really boring. But you can automate it all. It's okay. So what problems do you have that you want to try and automate? Because we'll try and automate it for you. That's what I want to talk about.
We just need more GPUs. I think that's the... it just really come to a point where like we can, given enough sampling, we can solve any problem in the field. So we just need more compute power. It's pretty much.
Okay, maybe this is not my main point, but I was thinking in the last talk that I'm a little bit pessimistic about standardizing biodata actually, because it might be the problem is we always want to innovate and we want to have better sequencers and better microscopes and anything. And then if you're incentivizing standardization, you're kind of incentivizing using the same things again. And then I guess it's problematic. And since it's also, you're always going to have people come in and tweak the machine because they're going to do something different. Then the standard's going to break apart then. But that's probably not what I want to talk about. I want to talk about, DNA and evolution I'm interested in. So.
So I think in the future we're going to be surrounded by AIs, agents. We're going to see hybrid teams everywhere doing research, doing stuff, and we have to prepare for that. So, and I think, yeah, I don't know if there is a new standard that's going to evolve besides English. Like, I think that's going to be I mean, I'm not the first to say that, but that's going to be the programming language, English, or just like French or German. And we have to prepare for that. So, yeah, I'd like to discuss that too.
Okay, wonderful. Well, then I will be getting the biotech speakers into the room that where I'm probably out having a coffee. And I'm going to ask you guys to hang around here in this room so people can find you. For the next 30 minutes, you have time to basically chat with your favorite biotech and molecular machines panelists about the topic that, you know, they already noted that they have an interest in talking about. And then we're going to break for lunch. So thank you so much for joining the second panel of today. I hope you found it fun. Please add more manifold questions and we'll see you at lunch. And I'm going to get your biotech speakers all the way back here. So we will have half an hour for that. Thank you so much. This was wonderful. Thank you.